So I'm going to wait a little longer just to give people a chance to show up. Reed is in the meeting and he's managing the recording, but he won't actually be here for the talk this week. So if I need to check if you guys can see stuff, someone else is probably going to say something. That's okay. Initially, I had a lot to talk about this week. At the top of the file. Instead of talking all of that stuff, what I did instead is I started with a bunch of utilities in this file already. We're going to go and look at those. We have to add a couple of type definitions first. And we'll talk about what they do, but I just didn't have enough time to sit here and write all of them, and we've and then we'll have the time to talk about implementing the actual, plenty of time for questions. You can just, there's a lot of errors in the file. That's because there's some type definitions that are missing and stuff like that. If I knew how to turn it off. Yep, okay, gone. So, okay, I'll just wait a few more minutes. I see, have you been to these meetings before? I think I maybe remember seeing you once. Okay, nothing. Okay, yeah, we're going to be talking about semantics again today, and so I just want to make sure that everybody's familiar with the idea. There's some semantics rules on the screen. But yeah, okay, I think I'll wait till 3:05 just in case anyone else shows up, and then get. So just in the meantime, if anybody has any questions, maybe about stuff we did last week or something, feel free to speak up. And interrupt me with questions at any time. I know I talk kind of fast and maybe that's a little bit daunting, but please, if you have questions, just interrupt me. It's a lot easier to hear you talk than to see the notification in chat and then have to open it. Yeah, we do have big step semantics for our language over here, but they're not changing this week. We're just talking about types. They'll start changing a lot next week when we start adding stuff. Because once we have the type inference engine in place, adding stuff gets real easy. And actually, it mostly becomes a parsing challenge. And so this part of adding, for example, let expressions and function application is just figuring out how to parse them. But okay. All right, so it's 3:05, so I'm going to get started. So you guys may remember last week at the end, I talked about types that have a quote unquote notion of sequencing. So I was talking about the either type that has its left and right cases, and I said people use the left case to keep an error and the right case to keep a success. And when you have a bunch of functions that return ethers, you can sequence them by just making sure that if one of them fails, then fails with the same error. And so there are lots of different types that have sequencing, right? For example, you could have a type that represents actions that have access to a state. And it's important that you do those actions in the right order so that each is the correct state and the actions after it, also see the right modified states if an action happens to modify the state. And so in Haskell, The word that we use for these types with a notion of sequencing is monad, which is kind of a scary word, but it comes from category theory, and it really just means has a notion of sequencing. And so there's a few of those I'm going to want to use today. So I want an exception monad that handles errors. I want a state. We're going to just use that so that we can get a counter. And I want what's called a writer monad, which essentially on the side keeps a list of things. So you can, and then the writer monad will accumulate it to the list, and then the list just go through the pain of making sure that the lists from separate actions are combined in the right places or accidentally dropping elements or whatnot. So that's mostly a convenience. And then we're also going to want a import. We're going to want a set data structure. A lot of names in that module conflict with names in the prelude. So, okay. I think first I will talk about some of the utilities that we have. So let's go down here-ish. Yeah. So I want to talk about first, then we'll talk about the semantic stuff on the side. Then we'll add the new types that we need and we'll implement it. So first of all, the idea of type inference is we have a program. We want to look at the sub-expressions of that program. So maybe a big expression is a like have the binding of the variable and then also the body of the let itself. X equal body in binding. And body X equal binding in body. And so the body and the binding are both sub-expressions. And we want to infer the type, the most general type if we can, of every sub-expression, and then make sure that all of the types match where they should. So we make sure the program type checks. What we're doing this week is to the language, these tie vars, so that they can represent any type, and we don't know what there is a mapping from type variables to types that makes the program type check. So such a mapping is called a substitution. So here we have a substitution type. And you can do a lot of things with substitutions. Importantly, you can apply substitutions to types. So here we have this function applies a substitution to a type. You can also apply substitutions to an environment, a type environment, that just applies the substitution to all of the types in the type environment. And then you can apply a substitution to a single type variable. So that looks up what the substitution maps that type variable to. If it doesn't return anything, though, it doesn't fail. It just returns the type variable. If there is a mapping for the type variable, then you return what it's mapped to. The other thing that you can do is composing. Composing is a little bit more complicated than you might expect, right? They were mappings from strings to values or strings to types. It's super easy to compose environments. You just smash the lists together and it works. For environments, it's a little bit more complicated because you have to make sure that the mappings in the first environment are coherent with the second environment. And what that means is that if there are types in the second environment that refer to type variables that, substitution, not environment. If there are types in the second substitution that refer to type variables that have mappings in the first substitution, we need to make sure that the type variables in the second substitution are substituted according to the first substitution, so that the type variables in the first substitution, the one that we need to do first, no longer appear in the second one. So this function just implements that. And so it implements that by applying the first substitution over the second one, and then computing the results. If you don't do that application, instead of compose, that the result is called merge. The merge function is useful in some cases. It's actually extremely useful for type checking Haskell code. The language that we're using is simpler for various reasons, and so merge is not useful. Okay, and then the other thing that you can do is you can delete a mapping from the substitution. I'm not sure if I actually used, oh yeah, I did use the delete function here. So, okay. So you might ask, okay, I'm talking about types, but I have two different things named types here. So we have monotypes, we also have polytypes. So what does that mean? So in Haskell code, a lot of the time in terminal for this, oops, hang on, I can't see. Stuff is in the way. Okay, there we go. So I can turn on this flags. So set print explicit for false. Okay, and so now you guys know the identity function. I can ask Haskell what's the type of id, and it will tell me that the type is a. So what that means is just some other type a, but a can be anything. So the term a is and then we call this a polytype, and we call it a polytype because it has quant variables. It's polymorphic, right? Could use this id function where a is int, but we could also use it where a is bool or where a is string, and it will work just fine. So it's polymorphic. And here, then what we would have is we would have a type variable which takes some specific value, like maybe it's int, maybe it's string, maybe it's bool, but we don't know. But it's only one of them. So it can't be both it can't be both int and bool. It's either int or bool, we just don't know which one, for example. Type variables like that are called scalums, but I'm probably not going to use that word again for the rest of the talk. So that's just some background knowledge, I suppose. So normal as opposed to polymorphic, which means many types. And so the only difference between monotypes and polytypes is that polytypes have some quantified variables. So if we go all the way back up to our type definitions here, I renamed our old data type to monotype. I did that in the starter code because it requires changing things in a lot of places, and I didn't want to just sit here looking for them for ages live, so I just made that change already. We have to add a new thing to monotype. Before we only had type constructors. Now we also need type variables, and so we're going to add tyvar, and we'll give a type tyvar, which is just type tyvar, which is just int. So each type variable has a unique name. That name is really just a number. And then we'll use our counter to make sure that we don't generate names for type variables that we've used before by using a counter. Okay, and then once we have those, we need polytypes. And so what is a polytype? It's for all some list of quantified type variables followed by the monotype that it quantifies over. So does anybody have any questions about that? This is just the kind of basic stuff that we need to get off the ground. Okay, so going back all the way down here. So we can see in order to substitute into a monotype, you just you apply the substitution to each type variable in the monotype, and then if you have a constructor, then you recursively go into the type arguments and do the same thing to all of the type variables that you see. For a polytype, it's a little bit different. For a polytype, we don't want to apply the substitution if the substitution has mappings for names that are quantified in the poly. Applying the substitution would mean we're fixing that type variable to the monotype that the substitution maps it to. But a polytype says it should work for all. So we want to hide types from the substitution. So that's what S prime is. S prime is the substitution, but without the quantified type variables. And then we apply the substitution to the rest of the monotype. And then the other thing is our type environments changed. So instead of having now they have polytypes, which should make sense. And so we use substitute polytype here instead of substitute monotype. In types, we have to occasionally talk about what are called the free variables of a type. And so that means the type variables that are not quantified in the type. So for a monotype, that's every type of all of the type variables that appear. For polytypes, if a variable is quantified, it's not free. So what we want to do is we want to get the free variables of the monotype, but then remove all of the quantified type variables. So we construct a set, and then we take the set difference. And then gamma is a type environment. We occasionally want the free variables of a type environment, and so we just do the same thing. We find the free variables of all of the polytypes in the environment, and we take the union. So, okay. With all of that background, I want to talk about unification. So that's called the unification algorithm. You might occasionally hear it referred to as algorithm W. That's specifically the application of the unification algorithm to a programming language called ML. PicoML is a smaller version of ML. So the way that the unification algorithm works of constraints. And a constraint is a statement that two types are the same. Usually it's that some type variable is equivalent to some type. So you'll see something like A unifies with int, for example. That's a constraint. The way that we write those constraints is with this tilde symbol over here. So we would write A tilde int to mean A unifies with constraint. Okay. Sorry, let me scroll down a bit over here. Okay. So our type inference algorithm is going to omit a bunch of constraints. So it will run over the sub-expressions. It will generate some new variables that we need to figure out what their values are as it goes. And then it will output a bunch of constraints about those variables. And then we have to solve those constraints. We have to figure out if there's a substitution that maps those type variables to monotypes so that all of the types work out, so that you can actually satisfy these constraints. And so the algorithm that does that, its semantics are given here. It's called solve. And so the way that this is written is solve takes a set of constraints as an argument, and it returns a substitution over here. And other than that, it's just written the same way as semantics. So this rule, the easiest one, is called delete. Delete says if something in the set says some type unifies with itself, then we can just throw it away. We get the same answer as if we just solve the rest of the set. Orient says that if we have some monotype unifies with a type variable, we can instead flip them so that the type variable's on the left. That's mostly convenience that we don't have to write the eliminate rule twice because it's a little messy. So we move type variables to the left whenever possible. The other rules are a little bit more complicated. So decompose says if you have a type constructor that takes some number of arguments, then solving that constraint is the same as just adding unification constraints for all of the arguments. So for example, simple example, if we have list of A unifies with list of B, then that's the same as solving the constraint A unifies with B. Slightly more complicated example, the function A unify, or sorry, the function type A to B unifies with the function type A to C is the same as solving the constraints A unifies with A and B unifies with C. And then we would use delete to throw away the A unifies with A. So that's called decompose. And then the other rule is called eliminate. So eliminate is the one that actually, really does the work. It properly gets rid of a rule and adjusts the substitution that comes out. So what eliminate says is that if we have a constraint that says some type variable A is the monotype tau, then what we do is across the rest of the constraints, syntax here means across the rest of the constraints, every time we see the type variable alpha, we replace it with the monotype tau across all the rest of the constraints. We solve the result that gives us sigma, the environment sigma, and then we return sigma, but with the additional mapping of alpha to tau, except it's not just enough to map alpha to tau. We have to also apply the substitution that we got back, sigma itself, to tau. And the reason for that is because some of the remaining constraints, as I said here, might refer to free variables that are in tau, and we need to get rid of them because we already solved them and we're not going to solve them again. So if we leave the references to them in tau, they're just going to stay there. And then that would be wrong. We would end up with type variables in our output that should have been mapped onto monotypes. Does that make sense? This is like the most complicated point of the unification algorithm. So if anybody's confused there, let me know.
Yeah, wait, could you repeat the beginning of the explanation of eliminate again? You kind of cut out a little bit.
Oh yeah, okay. So we have a set of constraints to solve, and one of them says a type variable alpha unifies with monotype tau, a monomorphic type. So what we do is in the rest of the constraints, everything else in the set, we replace alpha with tau everywhere. So these brackets mean substitute alpha constraints, and then we solve the resulting set. It gives us a substitution, sigma, and then we return sigma, but with this additional mapping. Is that better?
Okay, yeah.
Yeah, okay. And then I gave a little bit of an explanation here, so hopefully that helps a little bit if there was some confusion. The other thing, though, that you might notice is there's this side condition. None of the rules have side conditions. So I talked about what it means for a variable to be a free variable of a type. Notice we can only apply eliminate if alpha is not a free variable of tau. And so the reason for that is think about what the constraint A unifies with list of A would mean, right? What would that mean? Well, it means that the thing on the right, since A is equal to list of A, must actually be equal to list of A, etc. And the only way you can actually solve that constraint is if A is an infinite type, and we don't allow that. There are, as far as I know, no type systems where you actually can allow that. It just doesn't make sense. Any term with a type like that would always cause an infinite loop. You can't actually evaluate them. So we just don't allow it. We say that if that would happen, the program doesn't type check. We call it the occurs check because we're checking if alpha occurs in tau. And so actually, we can start by implementing that. So we want to check if a type variable appears in a monotype. We just return a Boolean. So we have type, we have a monotype, or sorry, we have a type variable and a monotype. And what do? We get the free variables of the monotype, and then we use this set member function, which remember I imported set qualified, so it's s member. And then I'm going to use backticks so that I can use it in fix, which looks fancy. And we check if the type variable is a member of the free variables of the monotype. And if it is, then that's a problem. So this is the whole implementation. The rest of the stuff that goes in this section is just an implementation of solve. So I don't think I have the type for constraints here. Yeah, okay. So the definition for constraint goes up here. So we're going to model a constraint just as a pair of monotypes. Occasionally, if people want to be fancy, you'll see them define it this way. Monotype. There we go. So this is exactly equivalent. This thing is isomorphic to a pair. It's just using the constructor name : tilde : instead of using a pair explicitly. I think that's fine. Thought about doing that, but I had already written some code, so I just left it as a tuple. It doesn't change anything. So our solve function now takes a list of constraints as its input. We're just going to model the set input as a list because if they're duplicates, we don't care. Also, there shouldn't be duplicates. And then we're going to return either a string. The string contains a type error if one happens, or we return a substitution that solves the substitution. And this return is the same as right for the if you remember from last week. So I'm just going to leave that as return. And then we have 4 rules and we can implement them each separately. So first we have delete. So first constraint is T1 unifies with T2, and then there's some other constraints. If T1 is equal to T2, then we just have to solve the rest of them. Does everybody see how that comes from the rule? We just throw away T1 and T2 if they're equal. Okay. And then let's see. I did these in a weird order in the code, but let's do it. So let's implement eliminate next. So for eliminate, the first thing has to be a type variable. The second thing is any monotype, and then there's the rest of them. Okay, what do we do? Well, first we have to do the occurs check. So if n occurs in tau, if the type variable occurs in the monotype, then we have a problem. And so I'm going to use this function throw error just for consistency with the code that I'll write later, the same as left. Can't construct, and this is the same way that Haskell would output the same error. Can't infinite type, and then let's say show var n unifies with show empty. And so actually in the code for this week, I wrote some prettier printing functions. We've been talking for the last few weeks about how the printing that our REPL does is kind of ugly, like it prints int val 5 instead of just 5. Before it was tolerable. After adding polytypes, it gets really messy. And so I wrote some prettier printing functions that help with that. But the thing is, in this particular case, in order to get a good error, the printing function has to know all of the type variables that might appear in the error so that it can print, actual names instead of numbers, and so that there are no conflicts. And so we can use those here. And at this point, I'm not talking about the unification algorithm. I'm just talking about some stuff for making nice errors. I'm going to indent it a little bit, though, because I need to put some other stuff in this where block later. So all of the variables that might appear in the message. And so that's n, as well as all of the free variables of the monotype. And then we'll write this pretty type function that just uses a helper function that exists further down in the file. You can look at that later if you want, to generate a pretty printing function. And then instead of show, I'll use pretty type for both of these. And then that will give us a much nicer error message. So for the rest of these, I'm just going to do that without explaining exactly what's going on. The important thing is that pretty type turns a type into a string. Okay. If the occurs check is, oh, there's a typo here. Can't construct infinite type. And then just to make space, I'll put that on a new line. Okay. If the occurs check is satisfied, then we don't need to throw a message, right? Then we actually need to do something. So now we're going to say do. So we'll start by getting the substitution that solves the rest of the constraints. So remember, we have to throw away, or not throw away. We have to apply this map or replace alpha with tau everywhere in the rest of the constraints. And so we will modify rest to do that. And then what do we return? We return sigma, but we want to throw something new on the front. So on the front, we want to stick, let's see, a mapping from n to the monotype, but substituted according to sigma. Okay, everybody see how this comes from the rule? So we have sigma, but in addition, we map the type variable, this is alpha in the rule, to sigma of the monotype, okay? And now the challenge is we just need to figure out how to define rest prime. So rest prime is all of the constraints, but alpha replaced with tau everywhere. And so to do that, what we want to do is each constraint is a list of monotypes. We have a mapping from one type variable to another monotype. Everywhere in any constraint that we see that type variable, we want to replace it with tau. Well, what is that? That just means we're applying a small substitution, the substitution that maps alpha to tau, to every monotype in the constraints. And so what we want is we want to map a function that substitutes in both elements of a pair over the rest of the constraints. How do we define subst both? Well, it takes a pair and it applies our substitution to both elements of the pair. And what is our substitution? It's the function which substitutes a monotype according to the mapping from n to the monotype. Okay. So this is the whole rule. Does anybody have any questions about this? This is the messiest rule. So compared to this, the rest of them should be pretty straightforward. Okay. All right. So then after that mess, we get a really easy one. So orient says if we have a monotype and a type variable, as opposed to the other way around, followed by some other rules, then all we have to do is solve the same rules, but swap the type variable and monotype. So move the type variable to the left. And then the other rule is decompose. Oops. Okay. So decompose says, okay, this pattern is going to be a little bit messy, so bear with me. Decompose says if we have two type constructors, so remember the name of the type constructor is A, and then the type arguments are the A's. And so we have type constructors A and B with arguments A's and B's, and then some other constraints. There are two cases. So if A is equal to B, that corresponds over here with the fact that we have the same T on both sides of the unification constraint. So for example, if A and B are both int or are both list, that's good. But if one of them is int and one of them is list, that's bad. So if these are equal, then all we do is we zip up the A's and B's into a new list of constraints. So we constrain that the first argument of A is equal to the first argument of B, etc. And then we, oh wait, no, inside the parentheses. And then we tack that onto the rest of the constraints and we solve that. If A is not equal to B, then we're going to raise an error. And so again, we use this throw error function. And how did I write this? Couldn't match expected type. And then I'll use this pretty type function again. And then we'll line this up. I think it's there with actual type. Yeah, that looks right. Pretty type TB. And so this gives us a nice kind of error message. But again, in order to use pretty type, we need to tell it the scope and use that helper function. So the type variable scope here is all of the free variables of TA, and then we take the union with all of the free variables of TB. Interesting. Okay, the diff that I'm writing this code off of dropped the TB off the end of that, but it definitely needs to be there. Okay, and then we call the same helper function and at the scope. Okay, so this is the whole solver. The solver takes a list of constraints. It outputs a substitution that solves those constraints. And I wanted to start with this part just because this is like really the meat of the algorithm. So now, or actually, I guess I should pause for a second and just check. Does anybody have any questions about any part of unification, this whole thing? Okay. If you happen to be in CS 421, MP6 is going to look a lot like the code that I just wrote. it won't be identical, but it's going to be really similar. It's a type inference MP and it uses the same algorithm, or at least a similar algorithm. Not sure. Anyway, so now, if you remember at the start, I imported a bunch of things and said, these are the different effects, the different types of sequencing that I want to combine for our type inferencer. So now I'm actually going to do that. So I want to make a type called infer, which handles all of keeping a list of constraints, throwing errors, and keeping track of a counter for, for fresh variable names. So the way that we do this in Haskell is those modules each export what's called a transformer, and the transformer adds the behavior that it does on top of some other behaviors. So for example, the one that will keep track of our list of constraints is called writer, and the transformer is called writer t. So I say, I want a writer t that keeps track of a list of constraints. And then I say, I want that to be on top of an accept t. So this one handles the error messages, where the error is a string. And I say, I want that to be on top of a state with an int. This one's not state t, this one's just state because this one's at the bottom. So this is the bottom of the stack. And then all of that returns an A. So this gives me a type that handles, again, keeping a list of constraints, throwing errors, and keeping a counter, a mutable counter, this int. And I don't have to give this any like monad type class instance or anything like that. I don't remember if I talked about that last week, but I don't have to do any of that because the library that I imported these from does that for me. So great, makes this super easy. So we need a couple of functions just to like, help us actually use this type. So first, we'll take this function called unify. We'll hand it two monotypes, and then it will emit a constraint. So it will add to the list of constraints that the first monotype has to unify with the second one. The function that adds to the list of constraints is called tell, and we want it to add the constraint T1 unifies with T2. So super easy helper function. The other one that we need lets us get out of this big, scary infer type. So what this one does is if we have some sequence of inference things that returns a monotype, we want to be able to get out of infer and get back a polytype. And the reason we want to get back a polytype is because for infer the type of a function like id, defined as let id type alpha to alpha, we won't know anything about, and we turn it into a polytype going to get to this in a moment. We'll do that for us. Close over. So, okay. I'm going to use close over, then I'll go back over there and talk about what it does.
Is he gone?
Yeah, he said he would disconnect and come back.
Hello, I'm back.
Hello.
Was that just me or did it drop everyone?
Yeah, I think
It's just you.
just you.
Just you.
Lovely. Okay, that's awkward. All right. Can you guys see everything again?
Yeah.
Okay,
A lot
cool.
better now.
Oh, interesting. All right. Okay, so what we have here, I don't know why this is called R instead of MT, but anyway, this is the result. So R is going to be a monotype. C's is going to be the list of constraints that we emit. And then in order to escape everything, we use a bunch of functions with similar names. So first, we need to run writer T. And so this takes our stack, remember, is writer T, list of constraint, blah, blah, blah. So this strips off the writer T constraint, or the writer T part of the type. And now instead of just returning a monotype, we get a monotype along with a list of constraints. But it's still wrapped up inside all of this accept and state stuff. So then we also run accept T. So that gets rid of the accept part, turns it into an either. But remember, there's an either up here. So I'll come back to that in a second. And then the last thing we do is we eval the state part, and then we need to give it an initial state, which for us is 0. So the result of all of this is we get an either, where the failure case is a string, and the success case is a pair of a monotype and a list of constraints. And so now here, this do block, the sequencing that we're using, is now just for either. So that this isn't in a do block for infer, this is a do block for either. And the reason it's a do block for either is because the next thing can fail as well. So now we want to get a substitution by solving our constraints, and that can fail as well. And then our final result is to just close over applying that substitution to the monotype. So we solve all of the constraints, we apply the substitution to the type that we returned, and then any remaining free variables we quantify. Okay, and so I said once I was done talking about that, I would go and actually describe what this function does. So here we have a bunch of utilities for type inference. You'll see this function used to be called type of. That's not quite accurate anymore, so I renamed it to signature. I don't know why Emacs thinks signature is a Haskell keyword, but it's not, so just ignore the fact that this is red. It should be orange, just like every other function name. It's nothing special. So yeah, this used to be called type of. Over here, we have the type declarations for ints, floats, bools, and strings. These are all monomorphic types. They don't have type variables. Over here, in a second, once we're done writing the rest of the inference engine, we're going to go add empty lists to the syntax of our language. And then next week, we'll talk about how to do non-empty lists. Lists are a little different because lists actually have a type argument. And so for this one, instead of just taking the type and turning it into, taking the monomorphic type and turning it into a polymorphic type by quantifying nothing, this time we actually do quantify the type variable. So we want to say the type of the empty list is for all A. And in fact, if I open GHCI here and I ask what's the type of the empty list, that's exactly what it says. So this should be a good sign. Okay. And so now there's a few important ideas for the inference algorithm. When we have a type like this for all 0, tycon list 0, if we see 3 empty lists in the program, we don't want to just say that each of those empty lists has the monomorphic type, the monotype, tycon list of 0, because maybe one of those lists is going to be an empty list of Booleans, and one of them is an empty list of ints. And if we use the type variable 0 for both of them, then that's going to cause a conflict because we can't unify int with bool. Does that make sense? So it's very important whenever we see a new empty list that we don't just drop the for all part. We want to actually make sure that we replace all of the quantified variables in this type with fresh variable names that we haven't used before. And so to that end, we have 2 functions to help. We have this fresh function, which gets the value of the counter, puts the counter +1, and then returns a new type variable using the old value of the counter. So first this will return 0, then 1, then 2, etc. And then we have this function called instantiate. And so what instantiate does is for each quantified variable of the type variables, it produces a new fresh type variable. And this is written a little strangely. It's just because this has to be done inside the infer monad. But map_m, you can see the type at the bottom, looks a lot like map for lists. And so TV's prime ends up being a list of new type variable names that we've never used before. We create a substitution that maps the quantified type variables to our new type variables, the fresh ones, and then we apply that substitution to the monotype. And so this is called instantiating a polymorphic type. You drop the for all and then get back just the monomorphic type, but the monomorphic type has fresh names that you've never used before and will never use again. And that's how you guarantee that there won't be conflicts. So this instantiate function is essentially how we deal with polymorphism. We deal with polymorphism by every time it appears, we just get rid of it and replace it with a completely fresh monomorphic type. And so this is pretty common in type system algorithms. You deal with a high power feature by rewriting it in terms of a low powered feature. So in this case, we rewrite our polytypes as monotypes. We also sometimes need to go the other way, where we have a monotype, but we really need it to be a polytype. And so what we do is we generalize it, but we generalize in a specific environment. So we don't always want to quantify over all of the free variables, because maybe one of the free variables has other references to the same free variable inside other types in the current type environment. And if we quantify over it, then they'll stop being related, right? They'll stop being the same variable name. And that would be a problem. If we have two references to the type variable A, and one of them unifies with int somewhere, it's really important that the other one also unifies with int, or else we're going to end up with types that make no sense. So generalize needs to know what the current type environment is. And what does it do? It quantifies all of the free variables of the monotype, except those which are also free variables of types in the environment. So we take the monotypes, or sorry, we take the free variables of empty, set difference with the free variables of gamma. So this is generalize. And then close over is a function that does the same thing, except it doesn't care about the environment. It just quantifies every free variable. And so to do that, we just call generalize with an empty environment. So this takes every free variable of the monotype, quantifies it. So, okay, with those tools in hand, we can now go rewrite our function that used to be called type check, but it's gone, it's not in this file, that actually recursively goes over, why am I doing this instead of just doing this? Oh, that wasn't even right. And that was too far. Okay, 200 was actually okay, yeah. And then it recursively goes over the whole expression and emits all of the unification constraints. So what do we have? Same as before, takes an expression, takes a typing environment. Now instead of returning a either string monotype, it returns an infer monotype. And now we have a bunch of cases just like we had before. And for this, we have rules, typing rules. And so these are very similar to the typing rules that we had before, except notice now instead of type of, it says signature. And also notice that we don't only take the signature, but we also instantiate it. So that comes back to what I was saying earlier. It's really important that every time we see an empty list, for example, we use a different type variable. And so I'm starting to run a little low on time. So I'm just going to implement these rules directly. We've basically seen them before, and they still come more or less straight from the code. So constant expression, we don't care about the environment. We instantiate the signature. If we have a variable with a name, now we do care about the environment. We look it up just like we did before, except now when the lookup succeeds, we need to instantiate it as well for the same reason. And when the lookup fails, we throw an error. Variable name not in scope. What's name? Okay, there we go. All right, and then the big one. So if exp, we have E1, E2, E3, gamma. Okay, and now you'll notice there's this new premise over here, this new type of premise that we haven't seen before. This says that we should emit two new unification constraints, that bool unifies with beta and that tau1 unifies with tau2. So first we need to get beta by inferring E1 in the same environment. Then we have tau1, E2 gamma, and tau2 from inferring E3. Then we want to unify bool with beta and unify tau1 and tau2. And then final result, we can return tau1 or tau2. It doesn't matter. In the rule, I returned tau1, so I'll do the same here. Okay. So this is almost the entire inference thing. The only thing that's left is this infer function returns an infer monotype. We'd really like a function that returns in either string or polytype directly. And so we'll just modify this, give an infer top function, which takes, that should be an exp gamma, and returns either string or polytype. And what does it do? It just calls run infer on the result of infer. Okay. So this is the whole inference engine. Using this, we could basically go and start adding features to the language really quickly because now we support polymorphic types. So there's a couple things we have to fix. First of all, down here, we still have references to type check. All we have to do is replace these with infer top. Nothing else changes, it'll still work. So after fixing that, I'm just gonna immediately go back. The other thing is that we have types for lists, but we don't actually have lists in our expression language. And so really quickly, let's just go and add those. Okay, so nilconst is already here. Okay, but we also need a value for that. So we could use nilval and consval like you would in Haskell, but actually just for ease of implementing our interpreter, we're going to do it this way. It's more or less the same. This one's just a little bit easier to work with. So we have that. Now we need to go down into the parser. And we have this parse exp case, or no, parse exp, parse const. We need to add a case for parsing lists. And then we need to add a function that actually parses lists. So we go all the way down here past parse string. And we say, okay, how do we parse a list? Well, our parser right now our language only supports empty lists. How do you parse an empty list? You parse brackets with nothing in them, and then you return an empty list. So that should be all of that. Let's see if I made any typos. So now I should be able to load this now with any luck. Hey, look, it works. Okay. And so if we, oh, wait, I can load it, but I did actually forget something. I can just go fix that. It's all the way down in the evaluator, which is further down than this. Yeah. So over here, we need to add a case for the empty list constant, which produces an empty list. Okay, there we go. Oh, whoops. Okay. So now, if we evaluate an empty list, what do we get? We get for all a list. And I could have written out the word for all. I thought using the for all symbol would be fancy. So I did. The other thing is in ML, unlike Haskell, you prefix type variables with an apostrophe. So it's pronounced tick a, but you can also just not pronounce the tick at all. So we have for all a list. We can type expressions like if true, then empty list, else empty list. Again, for all tick a list. We can still type expressions like this. In fact, that even evaluates the expression, yeah. But we can't type expressions like this. So this will fail because we can't unify int with tick a list. So that's good. That means our type checker is working. Similarly, if I do this, can't unify bool with tick a list. And if I say, you know, maybe put unit here, empty list, same kind of error. Does anybody have any questions about any of this? Oh, the other thing is I can also do, for example, let x equal empty list like this, and now I have x defined as a polymorphic empty list. So we do really have polymorphic values now. So yeah, sorry, I kind of rushed to add the empty lists to the language just because I only had 10 minutes. But I wanted to be able to demonstrate in our interpreter that this type checker actually works. So yeah, does anybody have any questions about any of this? I don't have anything to do today, so I can sit here for a while if I need to. Okay, doesn't seem like it. So this exact file that I just wrote won't be committed to the GitHub repository. But the version of it from before I started writing code, the version which has the utility stuff and the pretty printing stuff, but before I wrote the unify and infer functions and solve, that version is in the GitHub. So if you just want to look at the pretty printing stuff, you could maybe look at that. That might be a little bit easier than searching the bigger file. But then also the big file, my reference code is in there. And then also this week, I've started posting the semantics as well. And so this semantics file is in there. The other thing that I wanted to say is this omit premise is a nice convenience for making this rule look good. But it's not theoretically sound. The proper theoretical way to write this would be to say that every typing judgment also, as a side effect, produces some constraints. And then what we actually have to do is get the constraints from judging E1 and the constraints from judging E2 and the constraints from judging E3. And then the constraints from judging the whole if expression is the union of all of those, as well as the union of the set bool unifies with beta, tau1 unifies with tau2. I didn't want to write that out this week because it's not that messy, but it's a lot of symbols, and so it looks really scary. Unfortunately, it's not possible to properly type check let expressions unless you write it out the long way, because there are, in the correct implementation of let, one of the premises needs to refer to the constraints emitted by one of the other premises, and there's just no other way to do that. So in future weeks, I think I'm probably going to write it out the long way. And I just hope that having it done this way one time so that you can see what's going on and you can see where these constraints came from when we implemented the infer rule helps. But yeah, there are other type checking algorithms. They all behave similarly. So like the core idea is the same. Some other algorithms will actually solve the constraints as they're generated instead of waiting until the end. I specifically didn't do that because the code is way messier, but it's actually easier in a lot of cases to extend the algorithm when it works that way. Because not waiting to solve constraints means that you have some more freedom to do crazy stuff, because if you lose type variables, it doesn't matter. The constraints have already been solved. So Haskell actually does quite a few crazy things in its type system if you start turning on extensions. And so for Haskell, it's really important that they solve constraints while they're inferencing. For us, it doesn't matter, excuse me. And the code is quite a bit cleaner this way, so I went ahead and did it this way. But yeah, so it doesn't seem like anybody had any questions. So I think that's that for this week. Thank you guys for coming. If you're looking at any of the code over the course of the week or ever, and you have questions, just ask in our Slack channel. I don't post there ever, but I do have the tab open. So if someone posts something, I'll see it.
All right, sounds good. Thank you.
Yeah, sounds good. Thank you.
All right, see you guys next week.